Hello everyone, my name is Brett Meyer, and today I'll be talking to you about walking bout duration in persons with multiple sclerosis. So let's just imagine a time where remote monitoring would be important. I think one that can come to mind is COVID-19, where people may be afraid to come into healthcare settings. They might be unable to access their healthcare, or they might just be unable to afford their healthcare. And a solution to this would be technologies that we can deploy in people's homes, not requiring them to come into the clinic. And it is important to point out that this doesn't just happen in a global pandemic. This happens every day in rural and impoverished communities. So let's talk about why multiple sclerosis. So MS affects 2.3 million people globally. It is a neurological autoimmune disorder that's characterized by the demyelination of central nervous system axons, which leads to slowed sensory transmission, leading to numbness, tingling, and ultimately a high prevalence of falls. And in a given 3-month period, 56% of people with MS will experience a fall, and over half of these falls result in an injury. And it is important to point out that these symptoms are known to fluctuate in differing timescales. And this is currently assessed with biannual office visits, and symptoms are tracked at best with surveys and assessments. And the literature that motivates this shows that gait parameters can be robustly calculated at home in people with MS. It also shows that people with MS walk differently in clinical and home settings. We've also seen that fall risk can be accurately calculated in lab data, using lab data, but these models don't generalize well to home data. So we should try to investigate a little bit more into why that doesn't work. And studies have identified differences in gait parameters by walking length in studies with healthy adults and Parkinson's disease. So it's pretty clear that there is a need to understand what duration of walking at home most closely relates to measures of fall risk and clinical ratings to allow remote fall risk analysis and an understanding of symptom variability. So to answer this question and really just explore this, we grabbed a data set from my lab that has 39 subjects with MS. There were 12 male, 27 female. The average EDSS was 2.99. I'll explain a little bit what that means later. And 20 of these subjects were identified as fallers, meaning they have experienced a fall within the previous 6 months, and 19 were considered non-fallers. A neurologist came in and did an expanded disability severity assessment, and the subjects also answered several questionnaires on their own. The MSWS-12, which captures walking impairment, the ABC, which captures balance confidence, the MFIS, which captures fatigue, and the NSI, which captures sleep difficulties. And then after doing all this, we had the subjects do some things in lab, but then we sent them home with a sensor on their chest and on their right thigh, and this sensor was gathering acceleration for 48 hours, and we had just asked them to go throughout their daily life. So I started this project here with just a bunch of raw acceleration data. So the first step to do was just to classify this data classify the walking bouts in this data so we know when the people were walking. And just want to point out that classifying walking bouts and the extracting gait parameters blocks are in black because we're just going to treat those as black boxes for this class because I had made that from my previous work. But once we had classified the walking bouts, I didn't have a way to extract these gait parameters from this certain subset of this certain population, so I adapted a new script to allow me to basically use my existing script to extract these gait parameters from the different walking bouts. And then once I was able to pass that through and get gait parameters for each walking bout, I separated walking bouts into 8 seconds or less for short walking, 12 to 28 seconds for moderate duration walking, and 32 seconds or longer for long duration of walking. And it should be pointed out these are classified in 4-second intervals, hence the 8 to 12 being missing. And then after this point, we summarized the values for each subject using several different summary statistics and added in the clinical surveys and assessments for each subject in large summary tables. And then for analysis, removed missing values and ignored NANs for certain things. And at the end, we have some squeaky clean data to play with. So let's think about what we have for this data. 54% of the data, 54% of the at-home data was 8 seconds or less. 36% of the walking bouts were between 12 and 28 seconds, and 10% of the walking bouts were greater than 32 seconds. So if you think about this kind of makes sense that when you're walking in your day-to-day life, you probably don't have any prolonged walking periods. You probably don't have many prolonged walking periods greater than 8 seconds without stopping, turning, or changing directions. And then if we look at our subjects themselves, they're pretty low to moderately impaired study population with an average EDSS of about 3, like I mentioned, which anything above 6 is considered severely impaired. And their average balance confidence is 82 out of 100, and their average walking impairment is 26 out of 100. So this just means they rate themselves as pretty confident in their balance and pretty pretty low walking impairment. The gait parameters we extracted were swing, stance, and step duration, as well as duty factor to capture pace and cadence, as well as the RMS, the anterior-posterior direction of the chest sensor, and the medial lateral frequency dispersion of the chest sensor, and those both capture stability. And then we use summary metrics, so we could give basically one summary value for each participant for their 48-hour period, and we use mean, median, standard deviation, max, min, 5th percentile, 95th percentile. And then again, fall risk was calculated using the lab fall risk model discussed in the paper in the related work section. So looking at the how the gait parameters vary just by bout length, we found several significant differences using Bonferroni correction and rank sum tests, and they were significant across all groups. So meaning 8 versus 12, 8 versus 28, or 8 versus 32, and then 12 versus 32 for step, stance, and swing duration, and medial lateral frequency dispersion. And there were significant differences seen in duty factor and RMS AP, but this probably means nothing to you, so let's look at some plots and see if we can figure out what that means. So just looking at this plot, we see the plot on the right. It's pretty clear that the step duration decreases as walking bout duration increases. So this means that people with MS tend to increase their cadence, likely walking faster, for longer walking bouts. If we look at, again, the plot on the right, we see a slight increasing trend with walking bout duration, and the plot on the right, slight decreasing trend with increasing walking bout duration. So this means that people with MS tend to increase their motion in the direction of travel, so the anterior-posterior direction, and reduce their side-to-side motion with longer walking bouts, which again makes sense. We're reducing our side-to-side sway and no longer sauntering. Looking at how it correlates with the clinical parameters, we saw several significant correlations with the 8 seconds or less. So we saw 19 significant correlations with these values, whereas we only saw 1 for 12 to 28 seconds and 1 for greater than 32 seconds. And it is interesting to point out that every single survey is represented in the significant correlation in the 8 seconds or less, whereas only 1 is represented in each 12 to 28 or greater than 32. And then if we look at fall risk, there were actually no significant differences if we just compared the values of the fallers and the non-fallers for any bout duration. But if we compare the values to see how the calculated fall risk compares to the lab fall risk model, again, 8 seconds provided the best results, with shorter bouts, again, providing greater agreeance to in-lab walking fall risk calculations. Then we just did a bunch of modeling here. So the summary gait features were used to classify fall risk for people with MS. The features were z-score normalized. Davies-Boulden feature reduction was used with threshold of 6 to take us from about 42 features to about 30. Principal component analysis with a threshold of 95% variance was used to reduce us to another 8, to cut us down to 8 features, or principal components. And then the models were trained with least one subject out validation. In random forest, logistic regression, k-nearest neighbors, SVMs, and decision trees with the models I chose to use, and I optimized all of these using a random grid search. And if we look at the table on the right, we see, looking at the AUC column, that the performance, again, was best for 8 seconds or less compared to all the other ones. And that, again, gait parameters classify fall risk best when calculated from short walking bouts. So let's just wrap this up. So the main takeaways from this are cadence and stability of walking increase with increasing walking bout duration, as well as short walking bouts correlate with clinical assessments and surveys best, and fall risk is best classified with short walking bouts. Comparing to what this shows in the literature, this is in line with what they found in the Parkinson's disease study. However, there is nothing to compare to in MS. And then lastly, this being a class project, there's always a lot more we can do. In the future, I would like to look at how these parameters vary from time of day, as well as day to day, and as well as how they compare from their initial and 6-month assessment. Thank you for watching, and have a great day.